Captions in English, please. So this is the 6th video on chapter 12, and it's on exceptions to the octet rule and resonance structures. So not all atoms have octets. We already have seen how hydrogen only needs a duet to be like helium. It needs only 2 electrons around it. Beryllium and boron are also exceptions because they are small atoms. They have very few protons and electrons around in their nucleus and an electron cloud. And so beryllium will only need 4 electrons and boron will need only 6 electrons. So these are the main exceptions. Let's look at an example of beryllium, BeH2. Beryllium brings group 2A, so brings 2 valence electrons, and then each hydrogen brings 1 valence electron times 2. So that's 2 electrons from beryllium, 2 electrons from the 2 hydrogens, that's 4 electrons in total. And so the structure of BeH2 will look like this. Beryllium is surrounded by the 2 hydrogens, and there is no lone pair on beryllium. And notice how there is only 4 electrons around beryllium, and this is a stable configuration for beryllium. So this is showing you the model of the molecule. And let's look at an example of compound of boron, BF3. So the Lewis structure looks like this. And if we count, we have 3 single bonds, so 6 electrons around boron, and we have 3 lone pairs on each fluorine, and so that's 3 lone pairs times 3 fluorine, that's 9 lone pairs, so 18 electrons there, right? 6 times 3, 18 electrons as lone pairs on fluorines, plus the 6 from the boron, that's 24 electrons in total. And so that's a stable configuration for boron. It only requires 6 electrons around it, and it's stable this way. And so that just shows you the model for BF3. So resonance structures. So a molecule shows resonance when more than one Lewis structure can be drawn for the molecule. And so resonance structures are 2 or more electron dot formula for the same arrangement of atoms. So for the same molecule, there are different ways of drawing its Lewis structures. You can see the example of the ozone, molecule of ozone below. Ozone is O3, 3 oxygens bonded together. And you can see how you can draw it one way or the other. And so we show a double-headed arrow between the 2 structures to show that they are, the molecule is flipping between the 2 structures. And so that also tells you how the structure, in nature, the structure that is observed for ozone is in between. It's an hybrid. It's not one or the other. It's something in between. So resonance typically stabilizes molecules. And you can see here that the difference between the 2 structures is just the location of the double bond, which goes from right to left. But it's really the same structure otherwise. So let's practice writing a resonance structure for NO3, the nitrate ion. So as always, the first step is to determine the total number of valence electrons. So we have 1 nitrogen from group 5A brings 5 electrons. 3 oxygens from group 6A, they each bring 6 valence electrons times 3 atoms of oxygen. So that's 3 times 6, 18 electrons from the 3 oxygens. And then when you have a polyatomic ion like this, you need to pay attention to the fact that there is a charge of -1. And so that 1 negative charge means there is 1 electron in excess in this structure. So you will need to add 1 electron to the total. So the total number of valence electrons for NO3 -1 is 24 electrons, right? 18 plus 5 is 23 plus 1 is 24. So the second step is to determine the arrangement of the atoms. And so as always, when you have a formula where there is a single atom as first in the formula, it's going to be the central atom. So here, nitrogen will be the central atom, and then it will be surrounded on 3 sides by an oxygen. Third step is to attach each bonded atom to the central atom with a pair of electrons. So here it's already drawn as lines. And remember, our line represents 2 dots. So this way we have used 6 electrons from the total. So 24 minus 6, we still have 18 electrons to distribute. So the fourth step is to place those remaining electrons using lone pairs or multiple bonds to complete the octets. And so we calculated that 24 electrons, we started with minus 6 electrons for the 3 single bonds. That's 18 electrons remaining. So we will use those 18 electrons to do lone pairs on the oxygen, because you need to do lone pairs on the outside atoms first. And so each oxygen has 2 electrons from the single bond. And so we can give them each 3 lone pairs. So you give 3 lone pairs to each oxygen. That's 6 electrons plus the 2 from the single bond. That's 8 electrons around them. So each oxygen this way will reach an octet. And by doing this, 3 times 6 electrons per oxygen, that's 18. So we have used those 18 electrons that were remaining. So the remaining 18 electrons are placed as lone pairs on the 3 oxygen. However, this does not complete the octet for the nitrogen atom. You can see it is surrounded by 6 electrons only. So one of the oxygen will have to share a lone pair. And either oxygen can do it. You know, it can be any of them. They are all similar in this case. So that means you will need to write 3 resonance structures for NO3, NO3 minus 1, the nitrate ion, because the oxygen that shares can be, for example, on the bottom schematic here, we have the top oxygen that shares and then has the double bond with nitrogen, or the oxygen from the bottom left corner, or the oxygen from the bottom right corner. So you see how the double bond changes from one oxygen to the other. The rest otherwise is the same. And notice how, because this is a polyatomic ion, an ion, we need brackets around the structures and show the negative charge in the upper right corner. So when you do polyatomic ions, don't forget to add those brackets and write the charge on the upper right corner. So NO3 -1 has 3 resonance structures.